All right, welcome back. Today, we're jumping into part two of our explainer on integration by substitution. We've got the basics down, and now it's time to see how this amazing technique can crack open some really complex problems. If you're ready to seriously level up your calculus game, you are absolutely in the right place. So here's what we've got on tap. We're going to kick things off with a core example, just to lock in the method. Then we'll run what I'm calling the gauntlet, a bunch of problems to really build up our skills. After that, we'll see how this stuff actually applies to real geometry problems, and we'll finish up by tackling some exam-style questions so you're ready for anything. Okay, let's jump right in with our first section, the core method. We're going to walk through a classic textbook example, step by step, to make sure we have the fundamental procedure absolutely nailed down. I'm telling you, mastering these steps is the key to everything else we're going to do today. Here is our warm-up problem, the integral of x divided by the square root of x plus 1 from 0 to 3. Now, you just can't solve this directly. That weird combination of x up top and x plus 1 under the root, that's our signal. That's the clue telling us we need substitution to simplify this thing. Every single definite integral we solve today is going to follow these 4 essential steps. But listen, pay super close attention to step 2. Forgetting to change your limits from x values to u values is, without a doubt, the most common mistake people make. Let's make sure we get this right from the very beginning. And here's how it all unfolds. We let u equal x plus 1, which means we can rearrange that to say x equals u minus 1. And just like that, our whole integral transforms. We change our limits to 1 and 4, we split that fraction, and suddenly we're left with a simple power rule problem that we totally know how to solve. We integrate, plug in our new u limits, and bam, final answer, 8/3. And now for section 2. I'm calling this one the gauntlet. We've got the core method down, so we're ready for the main workout. We're going to tackle a series of problems from exercise 8D that are designed to really test our skills in a bunch of different situations. Our first challenge is question 3, which wants us to integrate x squared over the square root of 1 minus x squared. Now, that structure, the square root of 1 minus x squared, that should be setting off alarm bells in your head. It's a massive clue, a classic sign that we need a trigonometric substitution. And sure enough, the question confirms it, telling us to use x equals sine theta. So we do the substitution. Our limits change, dx becomes cos theta d theta, and the denominator simplifies beautifully to cos theta, which cancels out. Awesome. But we're left with a new problem. How in the world do you integrate sine squared theta? This is a really common roadblock. Our first substitution worked, but it's led us to a new challenge that needs a whole other tool from our toolkit. And the key that unlocks this door? It's the double angle identity for cosine. This identity is absolutely essential. You have to know it. It lets us rewrite sine squared theta, which we can't integrate directly, as an expression with cos of 2 theta, which is something we definitely can integrate. So we apply the identity, we integrate that new expression, and we evaluate it at our new limits. Now that sine of 2 theta term very conveniently becomes 0 at both limits, which leaves us with a super clean calculation. And this gives us our beautifully simple final answer, pi/4. Okay, time for a rapid-fire round. Let's really focus on sharpening our pattern recognition, kind of like building up muscle memory. We're going to burn through the first 4 parts of question 4. For each one, the goal is to just quickly spot that key relationship that tells you exactly which substitution to use. Okay, let's break these down. In part A, you've got to break that cosine cubed into cosine squared times cosine. That cosine term is the derivative of sine, so that's your cue. Let u equal sine x. For B, the whole thing looks messy. A great strategy here is to just let u equal the entire denominator, in this case, 3 minus root x, to simplify the fraction. For C, letting u equal root x will clean up that denominator. And for D, look at the inner function of the cosine. It's x squared over 4. Its derivative is basically the x sitting outside. That's the perfect choice for you. Spotting that key relationship is the whole game. Let's keep the momentum going with the second half of question 4. Again, just focus on the structure of each problem. What's the giveaway? What substitution is going to crack this thing wide open? In E, you see secant squared x. That is famously the derivative of tangent x. That's not a clue. That's a billboard telling you to let u equal tan x. For F, that x squared plus a squared form in the denominator is a classic indicator for a trig substitution with tangent. Same idea in G, that a squared minus x squared under a root points you straight towards a sine or cosine substitution. And in H, we're given a more creative one to unlock it. The strategy is always the same: spot the pattern, make the substitution, simplify. Okay, to finish our gauntlet, we have question 5. This one might look a little intimidating at first, but just watch what happens with a really simple substitution. U equals x minus 2. The integral just transforms into 4 over 1 plus u squared. And that form should be ringing a bell. It's the standard integral for arctan. A simple substitution revealed a familiar function and led us right to the clean answer of pi. So, why are we doing all this? What's the point? Well, in section 3, we're going to put it to work. Let's see how this powerful technique is actually used to solve real, tangible problems in geometry, like finding areas and volumes. All right, here are the curves for our next 2 problems. In question 7, we're going to take that first curve, spin it around the x-axis, and find the volume of the 3D solid it creates. Then, in question 8, we'll find the total area trapped by that cool wave-like curve. I'll tell you right now, both of these would be pretty much impossible without substitution. For question 7, we need to integrate pi times y squared. That gives us pi times the integral of ln x squared over x. And here's the beautiful part. If we choose u to be ln x, what's its derivative? It's 1 over x, which is already sitting right there in our integral. It's a perfect match. The problem just simplifies down to pi times the integral of u squared, giving us a final volume of pi over 3. How cool is that? And it's a very similar story in question 8. To find the area, we need to integrate this function. So we choose u equals cos x. Why? Well, because its derivative is negative sine x, and we have a sine x term right there ready to be substituted away. This crazy-looking thing just collapses into a simple integral of e to the u, which is one of the easiest integrals you could ever ask for. And that brings us to section 4, the exam challenge. Because look, in a test situation, the biggest skill isn't just knowing how to use substitution. It's knowing when to use it, and maybe even more importantly, when not to use it. Just take a look at these 2 integrals. On the left, a simple polynomial. You integrate this term by term, no substitution needed, don't overthink it. But on the right, we have a composite function, e raised to the power of x to the 4th. And crucially, the derivative of that inner function, 4x cubed, is sitting right there on the outside. That is a flashing neon sign screaming, use substitution. Let's look at 3 more examples to really hammer this pattern home. In the first one, we've got the function 2x plus 1, and its derivative, 2, is right there. In the second, we have the inner function 3x, and its derivative, 3. And in the third one, which is a little trickier, the function ln x is in the denominator, and its derivative, 1 over x, is also there. The pattern is always the same. Find that function and its derivative pair hiding inside the integral. Okay, we have covered a ton of ground. So for our final section, let's just boil everything we've learned down into a simple, practical toolkit of key strategies that you can apply to any problem you face. Here it is, your strategic checklist. First, you've got to become a pattern spotter. Always be looking for that function and derivative pair. Second, if you have limits, you have to change everything, the variable, the dx, and the limits. Don't be that person who forgets. Third, have your trig identities ready to go, especially the double angle formulas. And finally, always remember the goal. If your substitution doesn't make the integral simpler, you probably picked the wrong u. So what's the big takeaway from all this? Integration by substitution isn't just a trick for solving problems in a textbook. It is one of the most powerful, most versatile tools in all of calculus. And when you start asking yourself, what other complex problems can this technique solve, whether it's in physics or engineering or even economics, that's when you know you're taking the first step toward true mastery of the subject.